Hello everyone. This is lecture 10.2 of the GPU teaching kit. We'll be presenting a work inefficient scan kernel.
The objective of this lecture is for students to learn to write and analyze a high-performance scan kernel by using a technique called interleave reduction trees so that they can fully utilize the memory bandwidth. And they would also practice some subtleties in thread index to data mapping. And we would be using barrier synchronization to coordinate the activities of threads in a single thread block. And then we would be learning how to perform work efficiency analysis. Recall that we mentioned a naive parallel scan algorithm at the end of the last lecture. The problem with that naive algorithm is that the worst case execution time among threads is going to be the same as the sequential execution time. Therefore, we are using a lot of parallel resources without any performance gain. Here we show a better parallel scan algorithm that would actually have performance improvement over sequential algorithm. What we do is we load all the input elements into an on-chip shared memory, and then the threads will jointly perform reduction trees for every output element. Here we show the first iteration of the reduction tree where all the threads will add its own element with the neighboring element. During the second iteration, each thread would add its temporary sum to the temporary sum that are two elements away. And then it would continue. During the third iteration, each thread will add the temporary sum at its position with the partial sum that are four elements to the left. And as we can see that some of the thread positions will not have temporary sums that are four elements to the left. That means that these elements are already the final output value. As we can see from the top to bottom, after the first iteration, there are two elements, xy0 and xy1, that are the final output value. After the second iteration, the first four elements are of the final value, and after the third iteration, all the 8 elements are of the final value. This brings us into the topic of handling dependencies during these iterations. During each iteration, each thread is adding the temporary sum with the temporary sum that is of certain number of positions to the left, and it's going to override the value in its own position. This means that each thread can override the input of another thread. If we look at the first iteration, thread 1 is going to be adding value 3 to its own position of value 1 and generate value 4. And keep in mind that thread 2 will actually need to have its input value from the thread 1 position. It's adding that 1 value to the 7 value to generate 8. So thread 1 can actually be writing that value 4 into the position where the input of thread 2 is coming from. So if we don't carefully coordinate the activities of thread 1 and thread 2, thread 1 could override the input value that thread 2 is dependent on. So this tells us that we need to have barrier synchronization each iteration to make sure that all the input values have been used or secured by their neighbors. And also, before we proceed to the next iteration, we need to make sure that all the input values have been properly generated. So we see that at every iteration, we will see the pattern where we see a barrier synchronization to ensure that all the inputs have been properly generated. and then all the threads will proceed to secure their input values, and then we do a barrier synchronization to make sure that everyone has done so. And then after the barrier synchronization, all the threads would proceed to perform addition and write output based on the input value they secured in the second bullet. This brings us to the work inefficient scan kernel shown on this slide. When we enter the kernel, the threads will collaborate and load the input elements into the on-chip shared memory location. This is done through the familiar pattern of generating the data index I, and then use only the threads that are whose I value is within the valid range of data would load xi value into the xy thread idx.x position in the shared memory. And then we enter the reduction tree loop, where we start with stride 1. This is where the first iteration, where all the threads will be adding the xy value in its position to with the xy value that is one element away. And we need to first do a barrier synchronization to make sure that all the inputs are in place. Then we will do a secure assignment by loading the xy value that is from its left neighbor into a local variable that is thread private, so that we secure the value into that IN1. And we do a barrier synchronization to make sure that all the threads have already secured their input values before we proceed and calculate the sum of the xy element in the thread position with the value that we secured from the left neighbor. And then we we iterate to the next iteration. We would increase the stride size by a factor of 2, and so now the second iteration we will add the temporary sum of the in the xy position with the temporary sum that is 2 elements to the left, and then we would continue to iterate the third iteration and so on. And after we finish the loop, there's a barrier synchronization to make sure that all the threads have completed their addition in the final iteration. And then all the threads that are whose data index are within the valid range will write out the output value to the Y array. Now that we know how to write the kernel, we can analyze the work efficiency of the kernel. This scan kernel will execute log n steps or log n iterations to calculate the output for n elements. And it is a improvement over the sequential algorithm where the loop is going to iterate n times. So we have reduced the number of iterations from n to log n for a reasonably big input array. Let's say with 1,024 elements, we have reduced the number of iterations from 1,024 down to 10. However, we also need to calculate the amount of work that we need to do in order to enable this parallel execution. If we look at the amount of work that each iteration does, each iteration will do decreasing amount of work as we increase the number of iterations. During iteration 1, we will be doing n-1 additions, because only the thread 0 will not participate in that first iteration. And then in the second iteration, we will be doing n-2 additions. The first 2 threads will not participate in the second iteration. And then 4 threads will not participate in the third iteration, and so on. If we add up the amount of work or the number of additions that we're doing for each iteration and complete that expression for all the iterations, we would find an expression of the total amount of work to be n times log n minus parenthesis n minus 1. And so therefore, the amount of work that we're doing for the parallel algorithm is order n times log n. It turns out that this scan algorithm is not work efficient because in the sequential algorithm, we're only doing the work that is of order n. So if we have n elements, we will be doing n additions. So on the surface, we only added a factor of log n. However, in practice, the factor of log n can actually hurt. If we have 1,024 elements, the log n is going to be 10. So we actually blow up the amount of work by 10 times. Whenever we have a parallel algorithm that increases the amount of work significantly, we can easily have a situation where if we have limited execution resources, the parallel algorithm can actually execute more slowly than a sequential algorithm. And this is oftentimes the case when we have work inefficient algorithms executing on limited amount of resource hardware. GPU programming. This is the end of the introduction to the toolkit. Thank you.